Okay, so usually how I like to start the class is I take questions on the homework. So if anyone has questions on the homework, we will start there and move on. Try to do it quickly. This is homework for 10.1. $37. Okay, what was 37? Oh, you have a printout? Find the distance between x squared plus y squared plus z squared equals 4 and x squared plus y squared plus z squared equals 4x plus 4y plus 4z minus 11. Okay, ideas? Yeah?
On the right, you squares and make that into the equation for a circle or a sphere.
Okay, so this would be x squared minus 4x plus y squared minus 4y plus z squared minus 4z equals minus 11. So what would we get here?
X squared minus 4x plus 4, and they're all the same. So it's y squared.
So you're going to have x minus 2 all squared plus y minus 2 all squared plus z minus 2 all squared equals, this would be minus 11, but you're going to add 4 3 times, right? So this is plus 12, which is 1. Okay, so now that you know that, so we know here the center is what? The origin. And the radius is 2. Here, the center 2. The radius is 1. Okay, so how do we find the distances between these guys?
Well, I was confused. Does that mean the difference between the centers or the difference between the sphere itself?
The sphere themselves. Right. So this, by the way, again, that's a matter of a region. See, this is an equal sign, meaning this is describing the skin of the surface, right? The center doesn't exist technically. It's a hollow sphere, right? If we even could want to consider the center, we put like an inequality here, less than or equal to. Right? So once you have an equal sign, it means you're talking about the outermost region. So we have 2 spheres here. And in general, when I say distance, I mean the shortest distance between the 2. How do we figure that out? Yeah?
Isn't the distance between the centers minus the radius?
Right. The shortest distance is going to hit the centers. So I can find the distance between the centers and then subtract the radius. This one, let's say that's the one with radius 2, and this is the one with radius 1. Find the distance between the center here, subtract 3, basically. So how do we find the distance between centers? How would you find that?
Yeah, the distance one.
Just do the distance one. So what that's going to be?
2 minus 0 squared. Plus 2 minus
2
0
minus
squared.
0 squared plus 2 minus 0 squared plus 2 minus 0 squared. That gives us what?
Radical 12.
It's radical 12. Or you can think of that as
2
radical 3. This means distance between spheres is 2 radical 3 minus 3. Yeah.
I'm just wondering, for like the classes of squares, you like simplify it on that step up at the top. You don't take the x minus 2 squared, y minus 2 squared. You know what I mean?
Yeah.
Right there.
Yeah. What about it?
12. Like with part.
Yeah.
You did that, you like use points. Is that the same with you?
I don't understand.
You lose points for skipping a few steps because.
Well,
Oh, like I have to show that I added the plus block?
yeah.
I don't care.
Okay.
Okay. Show enough steps so I know what you're doing? Like, I assume you can figure out how to use it. Like, it's not, to get from here to here is not something you could sort of just guess and not really know what's going on.
Yeah.
Like, I would think to go from here to here, you'd know that you had to add 4 3 times.
Yeah.
You know, it's not something that you, like, can stumble on. Yeah.
I just want to make sure, because I was also confused when you did the same thing with the distance, like 2 square root of 3 minus 3. Is that minus 3 made up from like the
From here, the
radius?
centers.
Okay.
This is, the distance between the sphere is going to be the distance between the centers minus the radii. So that 3 comes from the 2 on the wall. Other questions? Yes.
Number 35.
35. What does it say? Write inequalities to describe the region. The region, all points but not on the spheres of radius r and r. So I have 2 spheres here. One has radius r, the other has radius r. I want the set of all points in between them. Oh, that was 33. Okay, hold on. The equation of all points equidistant from what points we have here. 1, 5, 3. And 6, 2, minus 2.
Yes.
Ideas?
Like you make up any point with coordinates x, y, z.
Right, so taking the point, an arbitrary point to be x, y, z. So we want what happened? What do we want?
Well, the distance from a to this point is be equal to.
The distance from this to this must be equal to the distance from that to that. The distance from this to this is what? I want x plus 1 squared plus y minus 5 squared plus z minus 3 squared. I want that to be equal to x minus 6 squared plus x minus 2 squared plus x plus 2 squared. Y and z. Right? Solve that equation basically. So if you sort of simplify, what would we get here?
X squared plus
2x plus 1 plus y squared minus 10y plus 25 plus z squared minus 6z plus 9. So what do we have? Well, x squares, y squares, z squares will cancel from both sides. And now what? What will happen? So here I have 2x, and on this side there's a minus 12x. I can bring that over here. I'll get 14x. That gets rid of those guys. Here I have minus 10y. On this side I have 4y. Move that over here. I have minus 6y. Those are the y's. Here I have minus 6z. Over here I have 4z. Bring that over. I get minus 10z. And what are the numbers that we have? So let's see. On this side I have 36 plus 4 plus 4. Bring this over, so it's minus 1, minus 25, minus 9. What does that give me?
9.
It's 9? Okay, so this is it. 4x minus 6y minus 10z equals 9. So the points that satisfy this equation are equidistant. From A and B. What kind of surface do you think this describes?
A plane.
Plane.
It's actually a plane. Right, so there's like a plane. Right, so just a plane going right in between them. Right? Where this is here, it's perpendicular. In 10.4, I think it is, we'll actually get to see why that's the equation of a plane and how we can get to an equation of a plane in various ways. But yeah, that's a plane, and this would be its equation. But yeah, what all these numbers actually mean something. What it all means, we'll actually cover in detail later on. Other questions?
Number 9 is probably kind of easy, but I just wonder.
Oh, well, you sort of find all the distances, and if the sum of the two short distance equals the long distance, it's on a straight line.
Oh.
Right, so the idea is, so if you're given 3 points, how do you know they're on a straight line? The length of this must equal to the length of this plus the length of that. If they weren't on a straight line, like there was a kink, then the length connecting the two farther ones would not be the sum of these, because it'll form a triangle.
That makes a lot of sense.
So that's just the idea. So if you have 3 points, you find all the distance between each pair, and if there's 2 smaller ones add up to the longer one, it's on a straight line. Otherwise, it will not. Other questions?
Yeah, actually, I was confused with 27 and 28.
So it just says describe in words what the region is. Yeah, 27. What is that? X squared plus y squared plus z squared plus 32. 3. Yeah, we actually did something similar. What do you think that is? It looks like the equation of a sphere, right? X squared plus y squared plus z squared. The center is 0, 0, 0. The radius would be radical 3. But here we have less than or equal to. So now you have this sphere, but it's everything less than or equal. So to get to the out here, that's radical 3. But you don't just want the radical 3. You want everything less than or equal to. So it shades everything in. So basically what this describes is a solid sphere. So that's how you describe it in words. It's the solid sphere of radius radical 3 centered at the origin. 29.
Yeah, but before you go there, just one more time, because I just wanted to understand why is it a solid sphere? Like, the radical 3 makes it a solid sphere?
The less than or equal to makes it solid.
Less than or equal to means it's solid.
Right, so if you have x squared plus y squared plus z squared equals 3, right?
Okay.
You're talking about all the points that are a distance of radical 3 from the center.
Okay.
So that's just only the points here. But what if I want all points that are less than or equal to 3, right? So what if I want? I also want all the points that are this far from the center, and that far from the center, that far from the center, that far from the center. They're going all the way out to radical 3.
Okay.
So it's taking all the points on the inside as well.
Oh, okay, I understand.
Right, so it will be a solid. Yeah.
The person will be less than 3. Would it be all
Strictly less than 3, it wouldn't include the boundaries. So the boundaries would have written it with like broken lines. So it will be everything inside of this sphere. It was strictly less than.
I understand what it actually looks like, but if it was the other way around, like it was like x squared plus y squared plus z squared is greater than or less than greater than or equal to 3.
Right. So
Like, how would you
be
actually?
all of space except the
How would
sphere.
you like write that? If I understand like solid sphere, like how would you write
You
it?
couldn't really draw it.
No, how would you write it? Like if it like ask you like this
Oh,
question
in
and
words?
describe it, yeah.
Yeah, all of R3 except the sphere.
Okay.
So you would say R3 except. Boom.
Okay.
So R3 is the how we write the three-dimensional space. Yeah. That's the shorthand for it. Right, you can bring your homeworks to the front. Just pass them to the person in front of you until they get to the front here.
Professor, I'd like to give you this yesterday. Okay.
Do you mind, like, when we're leaving, I could take a quick photo of my homework so that, like, I can have something to look over the weekend, like a copy?
We'll talk about that after class. So we'll just move on. The next section it's kind of a long section, but it's not too difficult. It's just a matter of telling you a lot of definitions because we're going to be talking about this stuff. You sort of need to know what I'm talking about. So we're going to talk about vectors and some operations that we will be doing with vectors. Let's continue the rest of 10.2 vectors. What is a vector? Yeah?
Is it a line with direction?
We call it a quantity. It's represented by a line sometimes with an arrow on it. A vector is a quantity having both magnitude and direction. Right, so it's typically illustrated by arrows, right? So this is called the head or terminal point of the vector. This is the length or magnitude. Right? So the arrow is telling you what direction it's going in. This is the initial point. It doesn't matter where you base the vector. Vectors they're fluid. You can move them all around. You put them wherever they're convenient for you to put them, right? But you can draw them as arrows. We also can name them. using either bold letters, which in a textbook it'll probably be bold letters, or letters with arrows. Example, if you see me write on the board A and I put a little arrow like that, that is not just a variable, it's a vector, right? Meaning I'm thinking of it as a quantity, right? So I can have a vector over here, but I have another vector over here, and I want to distinguish them. I can say, oh, this is the vector A. It has this magnitude heading in that direction. I can call this the vector B, having this magnitude heading in that direction, right? So we can distinguish them by naming them, and if I'm writing them down, you'll see me put an arrowhead. It's very important that you put that arrowhead, because we'll be dealing with both kinds of quantities, scalars and vectors. So I need to know when something is a vector from when it is a scalar. Equally important is for me to know that you know when you're talking about a vector and a scalar. So don't write down a letter and be like, I knew it was a vector. Like, I don't know you know it was a vector. You wrote down the thing, there was no arrow. How do I know you know what you're talking about? Right? So be very careful. Make sure you know when things are vectors from when they're scalars. It's actually something students do mix up all the time. They don't know when they should be doing a vector and when they should be using a scalar. Right? Hopefully that becomes clear as we move on, but so for now I'm just talking about this is what a vector is, this is how we can draw a picture of it, this is how we name it, and that arrow is a very important part of the notation. Right? Let's continue. Another definition, two vectors are equal and that's literally all they need to be equal. So I can have a vector here, A, and I can move it over here. Once it's parallel, as it has the same length, I can also call this A. I cannot distinguish between the two. Once they have the same direction and magnitude, they are equal. They are the same. I can call them the same thing. Right? There's no difference. I can take this guy and move him over here. It's still A. Right? It doesn't matter where the arrowhead or the base is. It doesn't matter. Right? Vectors, we can move them around. So, what else do I want to say? Other notation. Suppose we want a vector connecting a point A to a point B. Right, so I have 2 points in space. This is point A. This over here is point B. And I want to create a vector, which we'll be talking about how to do that, that goes from A and hits point B. Right? So A is the initial point, B is the terminal point. The notation I can write for that would be A, B, and I put the arrow like that. Right? If I'm going from, if this is A and that's B, and I'm going in this direction, I would notate that be A and put it down. So you point the arrow telling you where you're starting and where you're ending, put the arrow towards that. And so that's another notation. We're going to be working with vectors a lot, especially in chapter 10. So it's something you have to, these are all notations you're going to have to get used to. You can also combine vectors. So we can add and subtract vectors. Right, so multiplication is sort of tricky. There are different ways you can multiply them. We will get to that in this section, but for now let's talk about vector addition. I describe this in words. Do I want to write all this out? Suppose u and v are vectors. With the terminal point of view being the initial point of v. Then the vector from the initial point of u to the terminal point of v is the vector u plus v. So, illustration. So let's say I have a vector u doing this, and then it connects to another vector v doing something else. Then if I go from the initial here and cut out the middleman, go all the way to that guy, this is the vector u plus v. Right? So I've combined these two vectors into one larger vector. All it does is it takes the shortest distance between the 2 points. Right? This is adding two vectors, just means combining them. The initial point of the first one hitting the final point of the last one. Right? So we can add two vectors. Diagrammatically, we can also do it algebraically, which we will get to. We can also do scalar multiplication. I don't think I defined this, but when I say scalar, what do I mean? The scalar is what?
Just magnitude, right?
A quantity that only has magnitude. Right? So for example, speed is a scalar while velocity is a vector. We can actually do a scalar multiplication. So we can say let C be a scalar, B be a vector, so you can take a scalar and you can just multiply it by a vector. You can just write C times U. This is the vector having same direction as V. But the length will now change. not necessarily the same direction. It might be the exact opposite or something. But you can actually change the length, is what I'm trying to say. If C equals 0, the vector CV, do I just want to say that? Has no direction. It's not really a vector anymore. We'll talk about the zero vector, how crazy it is soon. Sort of illustrate that. So let's say I have here the vector v. Then I could say something like, what would the vector 2v look like? Well, it just looks like v, but now it's twice as long. Or I might say, what does the vector 1/2 v look like? Just like v, except it's half as long. Or I can say, what does the vector minus 2v look like? When the scalar is negative, you get the same thing, except you now move in the opposite direction. These should all be parallel, by the way. So what happens is negative sign reverses direction. I believe we're out of time. Didn't really get anywhere. Yeah, so we have a few more definitions, but then we'll actually be doing some problems next time. So we'll stop there. Next class we have a quiz on Calc 2 stuff again. We'll probably have a quiz every day next week, so maybe 2 more Calc 2 quizzes, and then on Friday I'll give you a Calc 3 quiz on the stuff we've done. Other than that, we can end there, unless there are any questions.
Yeah.
Please make sure your computers are logged off on the way
How many
out.
quizzes will we have like throughout the whole semester? Will it be like good?
Maybe around 10.
Oh, just that?
It's almost going to be every week. We have like 15 weeks, like 4 tests, so it'll be like 10 or 11.
Okay.
I'm like,
Nice meeting you too, man.
Oh, well, you have to give it to me today.